Oh, okay, we can see.
You can see everything? Okay. Hello, everyone. Thank you for joining this new Link Media Speak Science seminar. Today, we're very lucky to have Hanwei. Hanwei, you were with us not that long ago. Now you defended your PhD in 2021, if I remember correctly, right? Yes. And so you were a student of Yanis, Teddy, and myself. And now you are a postdoctoral researcher in Marseille, and you work on the interpretability of deep neural networks with also someone who came with us years ago, Renan Secret. And you are working there in Marseille with Stéphane Ayesh and also with Yanis. Your current work primarily focuses on trustworthy AI, of course, about interpretability and adversarial security of machine learning tools. And so I'm very glad that you give a talk today. Thank you, Kassem, for having contacted Hanwei. And we are ready. We are ready to listen to your presentation. Go ahead.
Okay,
Thank you.
Thank you for Cassandra invited me, and also thank you for the introduction for Laurent. It's my honor to give this talk today. And today I would like to introduce the interpretability in deep learning, and especially my work optimizing Saliency map for improving interpretability. And I would like to first give some background about the interpretability methods and then go into my work. So as we all know, if we look at the state of the art papers, we found actually deep neural networks achieve remarkable performance in subtasks about self-driving cars, facial recognition, and analyzing medical data. But however, these works didn't use in the real-life applications. There are lots of reasons, but I think the trustworthy problem is a very big reason. Because all these applications is related to the human health and properties. No one wants to risk about that. So among the trustworthy problem, the interpretability problem is a very interesting one, because currently the machine learning don't like the 20 years ago. They're following some specific instructions. We just achieve these remarkable results because of we have lots of data. And if we want to understand why the neural network make the correct decision, it's just silence, awkward silence. To break this silence, there are lots of researchers start to investigate the interpretability methods, trying to understand what the neural network learns and how they behavior. Actually, if we look at the work in this domain, it's quite various, because the researchers work on this topic have a very different background. However, all these methods, we could describe them according to 3 dimensions. The first dimension is passive or active. The passive work is also called post hoc methods. So which means we didn't change anything about the neural network. We're trying to use some other techniques to provide explanation to explain how the model works. And the active means we're trying to modify the architecture or the training process of the network and to make itself have some interpretability. The second dimension is what type of explanation we could provide. There are four main explanations we could provide. The first is examples. So it's normally related to the prototype. For instance, we want to know why an image is classified as a cat. We could compare it with the most typical cat images. And that could be an explanation of the inputs. And the second is attribution. So which means we assign some importance score to the every component of the inputs, which telling us how much it contributes to the final prediction. And the third one is the hidden semantic. So basically, it means we're trying to understand what the neurons learns. For instance, we can craft a specific input which will only activate one specific neuron. Then these images could be explanation to what's the neural name. And the last one is the rules. So normally it's some decision tree or some rule-based rule sets. So it will tell us how the neural network make the decision as a whole. And the last dimension is the local and global explanation. The local explanations means we have explanation to every input. For instance, the attribution method is more naturally to be a local explanation. And another is the global explanation. So it's like the decision tree. It will be a more global one because it's not explain why the neural network made decision for a specific input, but explain it as a whole. So today I would like to focus on the post-hoc attribution method. Actually, this is the most popular category of the methods because first, the attribution is very straightforward to explain an input. And second, the post-hoc means we don't need to retrain the whole models. It's respectively cheap for all these methods. So the target of the post-hoc attribution method is trying to tell us which is the most important part of the input to support the model's prediction. For instance, as the images, we're trying to find the pixels, which is most important for the predictions. Such kind of the attribution, it have actually lots of names. Some people call it feature attribution, some people call it salience map, some people call it heat map. Actually, it's the same thing. And all these methods we could group to 4 different families: the gradient-based method, occlusion-based methods, learning-based methods, or CAM-based methods. So later, I will introduce these 4 different families one by one, and I will give an example. I'm not going to go too deep to the details. I just want to give you an idea how all these families works. So first is about gradient-based methods. So these methods have assumption that they think if we backpropagate from the final prediction to the input images, then the pixels which have the higher gradient, which means it's more important to the final prediction. But we know if we just do the backpropagate and use the gradients, it's normally very noisy and it might relatively very small. So to make it more clear and amplify this performance, there are lots of efforts in these methods is trying to make it more clean. So for instance, I introduce roughly 3 different ideas to say how they trying to clean this gradient. The first is backpropagate. So the main idea is this is the salience map of the layers. If the salience map, the features of the layers, so it's just feed it to the network and take some features. If it gets the negative values, which means these corresponding positions, the pixels corresponding to these positions didn't contribute to the final results. So they think they could directly put it to 0. So when they have this is the gradient back to this feature map, and then they could directly replace displace the features. If the feature is negative, they can replace this region's gradient to 0 to make it more clear. And for the DCOVNet, they have another idea. They think what matters is about the gradient itself. If the gradient is negative, which means it's not contribute much to the final result, and they just put all these values to 0 to make it more clear. And the last, the backpropagation, the guided backpropagation methods, they combine the 2 ideas. It's like if in the forward, the feature have the negative value or the gradient itself have negative values, they just put it all to 0. And then they just do this one by one until the input images so that they can get a salience map like this. It will be more focused on the edges of the features. However, lots of researchers in the explanation AI was argue that this method is more likely a visualization, it's not interpretability explanation. Because they thought if this could have some properties like fairness or robustness and stabilized. So the next family is occlusion-based methods. So the idea is they can take one images and they mask the different part of these images randomly. So they could create lots of copy or samples based on the original one. And then they feed all these samples to the network to get the prediction. And then they can use the very traditional machine learning methods to analyze the relation between the input samples and to the outputs. For instance, a very famous method line, what they do is first for images, they can calculate some superpixels and they treat every superpixels as one features. And then they try to randomly modify some superpixels to create lots of samples. It's like the point around, if the red cross is original images, then they just modify some superpixels to generate some samples around it. And if it's more close, then it will have the higher weights. If it's modified too much, then it will be some sample more far away and with lower samples. And then they directly use some K-lassos to calculate the boundary from this class to other classes. And then they use the weights of these classified lines as the importance score of each component. And in this way, they can see, okay, this regions is most important for electrical guitar, and this for the electronic guitar, etc. So this method is more fairness, but more reliable. But it's also more expensive because how reliable and how better, how good it is depends on how many samples you generate. And you normally generate hundreds or thousands samples for one images, so it's quite expensive. And the next is the learning-based methods. So the idea is quite simple. They're trying to propose another neural network to provide the salience map to explain another neural network. So they take all the features from the target classifier and they apply some convolutional layer and then concatenate all these features together to generate the mask. And then when they have the mask, they have two laws. One is they take the mask in, take the object, and another is take the mask out. It's supposed only the background. Their idea is if they take the objects, they should have the same prediction as original images. If they take the background, then the prediction should be not conclusive. So they try to maximize the prediction entropy. In this way, they learned a network which will help to generate such kind of salience map. The next group I want to introduce is about the CAM-based method. The CAM actually is referring to class attribute activation maps. They all original from the original CAM methods, the CAM papers. Actually, this paper is observation. They found if a network which have the architecture of the global average pooling and then fully collected layer, they can use the weights which is related to the specific class, like the Australian tarot here, to combine the feature maps linearly. And then they found they actually can get a salience map which highlights the region related to this target class, the Australian Terrier. However, not all the network have this architecture, but a lot of people inspired from this from this observation. They think actually the salience map have already learned some local features, and maybe this feature is quite semantic. They can just by combine them to have a good salience map. So the CAM-based method is trying to investigate how to propose very nice ways to combine all the feature maps to give us a good salience map. For instance, they can use the gradients, or they can use some other way to estimate the weights. So before to go into my own methods, I want to build a little bit the connection between the post hoc attribution and adversary attack. It actually, especially for the gradient-based attribution methods, we found it looks like a little bit like a noise, because it's just highlights edges and also have some noise. And if we look at the adversary perturbation, we could see there is some semantic in these noises. We can see some dog's face in this noise. Actually, it's because no matter adversary attack and all attribution methods, they're trying to find the key features. As the images, as an example, it means the pixels. The difference is adversary attack, they're trying to find the most sensitive pixels, which we just have the slightly modification, and we could flip the prediction. But for the attribution methods, they're trying to evaluate the importance of every pixels more fairly. So this connection made me think maybe we could transfer some knowledge between these two domains. For instance, if I'm thinking how we tackle the adversary attack problem, what we do is first we put the perturbation as a variable, and then we have a misclassification loss, and also a constraint that this noise should be as small as possible, or some other invisible metrics. Then we're trying to optimize this variable until it satisfies it. So why we cannot use the sum concept to find the best salience map? So for what we want for interpretability salience map is we want this salience map we need have the interpretability loss. And actually for how to make the interpretability loss, the learning-based methods could give us some idea. We could use the mask in, and mask out loss. And then another is what is the constraint of such kind of salience map? Of course, it doesn't make sense if we give some noise like this. So this kind of constraint is more like vague, but we can get some ideas from the CAM-based ideas. So I think because I agree with the assumption that the network already learned some local semantic regions in their salience maps. So if we could have ways to combine them, we might get a very nice salience map. And since each salience map have some continuous regions which have to some extent some semantic, and also the dimension of the feature maps is high enough. So normally it's, for instance, 512. It's have enough ability to express all the information. So the idea is I put the weights to combine the feature maps as a variable, and then I try to optimize it with some interpretability loss. And here the interpretability loss we use is the mask in loss. So which means if we mask the input images with salience map, so we should keep the most important region, the object region of the images. And the prediction of this mask images should be the same as the input images. So that's how we get this interpretability loss. But here there's some details. For instance, we don't want the weights to be very extremely large values everywhere. So we apply some softmax to make these weights like the possibility to combine all the features. And also, the feature maps normally have different resolution than the input images. So we need some upsampling to make them as the same resolution. And also we want the salience maps values between 0, 1. So 0 means this region is not important. 1 means this region is very important. We have to keep. And I allowed them to have some region which is between 0 and 1 to say it might not that importance. So just by optimizing these weights, we can get a quite nice salience map. Of course, in this work, we do lots of ablations to how to make the interpretability loss, how to do the upsampling, normalization. But here we just keep the most simple one, because I found the different version is just improve a little bit about the numbers, but the concept is there. So I rather to keep it simple. Here I would like to show some experimental results. So how we evaluate the interpretability of this salience map, we use some average job and some existing methods, metrics like average job and average increase. So what they evaluate is actually they take the possibility of the original images and compare to the masked images. And the job, average job, evaluate how much the mask decrease the confidence of the prediction, and average gain is the average increase evaluate how much it improve the prediction. So in this way, for average job, it's lower is better, and for average increase is higher is better. In this work, we also proposed a new one. It's called average gain. It's also trying to estimate how much the possibility increased by the salience map. We proposed it is because we found if we test the performance of these metrics in fake CAM, the fake CAM is just a salience map. It have one values everywhere except one the pixels in the up right corners. They just set that value to 1 or to 0, and the rest is 1. So basically, this salience map just didn't tell anything, and it's the same for every images. And they just evaluate the performance of this salience map according to average job and average increase. Actually, found it performs quite nice in average job and the average increase, because it's just slightly changed the results. That is not a fairness. So to investigate it, to improve it a little bit, we make the average gain. That is this have evaluate the same thing as average increase, but it's use the method like average job. We evaluate how the margin, the confidence drop by the salience map. And so this table is quite complicated, but I only want to focus on 2 things. One thing is the green box. So basically, the green box just saying that according to these 3 metrics, our OptiCAM performed the best and a lot. It's like no other methods could compare to our methods in these 3 metrics. The second thing is an interesting observation. It's in the red box. So the B here is actually the ground truth bounding box. So it's given by it's a human noted bounding box. It gives us where is the object. So we're trying to use it as a salience map. So the first line is we only take the objects, and the second line is we only take the background. And we are surprisingly found, if we look at these interpretability metrics, the neural network think the background will help them more to make the decision. So basically, the neural network will think the background is more interpretable. So which means the localization is not necessary means the interpretability, and the network learns something about from the background. So this idea could be seen more clearly from the visualization. So here we see for our OptiCAM, actually we found more regions than the other CAM-based methods. And also we will take some background informations, especially for these phase cycles. The other methods, they more focus on the objects itself. But for OptiCAM, it's also considering the children using the tri-cycle. So we think it's quite interesting discovery. And another thing we want to talk about is actually we evaluate our methods according to lots of different metrics. And one metrics we want to highlight is insertion and deletion, because this metric is widely used in all the post hoc attribution methods. So the insertion deletion is its evaluation metrics. What they're trying to do, for instance, for insertion, they have the salience map. They rank all the importance of the pixels according to the value of the salience map. And then what they do is they try to add most important pixels to the images one by one. And so basically they have a series of images, and then they feed all these images to the network, and then plot how many pixels they add, and what is the change of the ground truth possibility. And then this value is the average value of it. And the deletion is still the worst. They're trying to delete the most important pixels one by one and make this curve. So here, the most important information I want to show is also in this green box. The first is our OptiCAM is actually not performed quite well in this insertion and deletion metrics. The second, we found actually the insertion deletion gain and the average drop, average gain, average increase is two subsets of the metrics. And it's very hard for one method have nice performance on both metrics. For instance, our OptiCAM have nicely results in average drop, average gain, and average increase, but not likely result in insertion deletion. And the X perturbation methods, they achieve very nice results in insertion and deletion, but they didn't, they almost have the worst results according to average drop, average gain, and average increase. But I don't think this means a failure of OptiCAM. I think it might be more a failure of insertion deletion. We'll investigate our worst case in the insertion deletion. So, and then we compare it to the score count. So for instance, for our methods, we have much lower insertion deletion score than the score count in these images, but much higher score in average gain and average drop. And then we found actually all these images have a comment feature is our OptiCAM found several parts of the images. So here we have the highlight here, but for the score count, they're kind of focused. They only have this region, maximum 2 regions. So we run the insertion step by step. We found actually when we adding the pixels according to the score for score count. They were adding all the pixels around this region. So by 200 pixels, they could have some full region of this object. Then the network will recognize it and have a higher possibility, have a higher prediction, have higher possibility of this class. But for our OptiCAM, actually this region, this region, this region, and this region, they have the equally higher numbers. So when we insert 200, for instance, 200 pixels, there are several here, several here, several here, several here. So they have very spread piece of the pixels. Then it makes the neural network very confused. They cannot recognize it correctly. That's the reason why we have so lower score in insertion and deletion. But I don't think it's a failure. For instance, here we recognize more about the object worm face, and it's recognized less. But it's we have the lower score about these metrics. But I don't think it means we didn't find but the network will recognize with all this information. So that is the discovery of the OptiCAM about this work. And for the future, I would like first improve a little bit about the evaluation metrics for explanations. For instance, I found the most widely used metrics have some drawbacks, like the insertion deletion. It cannot handle the situation that they found some several highlight parts. It's like if they highlight the head and highlights the tire of the dog and the legs, then they will think the Saliency map didn't find the object. It doesn't make sense to me. And I would like to investigate how to improve their, how to evaluate the Saliency map more fairly according to this case. The second I think is quite interesting is we could use all this explanation to trying to guide the learning. Because currently we are still working on the post-hot methods. But if we're using all these methods to guide the learning, maybe we will result in a more interpretable and robustness network. And the last I want to investigate is some connection between interpretability and adversary robustness. As I mentioned before, I see there's some certain connection, and I would like to know if these two methods for these two topics could help each other, or they have some deeper connection between them. So that's about my talk. Thank you for your attention. If you have any question, please ask me. Thank you.
Thank you very much, Hanwei. Other questions in the room over there?
Yeah.
Or do you want to start? Yeah.
Go ahead then.
Okay, I think I have a question, but it's maybe it's very naive, but we already had some talks about interpretability and explainability, talking about NLP. And in this case, they use attention, because generally they use the like LSTMs or things like transformers, and there is like they try to use this as like by design interpretability, and it seems that what you're building with this OptiCAM, it looks a bit like attention weights, because you take the softmax of a vector and then you apply this to like feature maps, and it makes me think a bit like attention. I don't know if you have if you have thought about, and it's a very naive question, sorry.
Okay, thank you for your question. Actually, it's true. Because for attention, what they do is so this thing is not like it's not directly like this vector. What's inside the softmax is actually the time of the K and Q matrix. So basically, for that, what they do is they have the CLST token, and then they calculate the distance of this global CLST token similarity to each patches of the network of each patches, and then they use this to combine all the features they learn. So I think there's some similarity in the they have totally different theory behind it. So here I feel like the how attention works is they have this similarity calculate, and here for our method is more likely to have the random variable, and within it to optimize this interpretability loss. And it's true that there is a lot of people talk about why not directly use attention as a salience as an explanation, if it's better than the salience map. Actually, this discussion in the NLP is quite tense. So I can directly tell you the conclusion. They think the researchers from the NLP, they think if they can use some salience map methods, it will give the better explanation than attention maps. So here, actually, I personally do some experiments about the vision transformer, and my observation is if we just take the attention map of the supervised classification, actually this attention map is not give us much information. It's like everywhere and with some small buttons, and it's not really explainable. But if we take the attention map of self-supervised learning, then it really looks more explainable. And also the metrics also tell you it's more explainable. I hope this answers your question.
I had to cut the microphone in the room because it was making some noise. So maybe if you want to continue, you get to switch that thing on again. Some other questions in the room or elsewhere?
Yes, I have one.
Go ahead,
Is that okay? So I come from the backdoor point of view with regards to the security of AI. And I'm wondering about whether or not the method could be applicable to in some sense, to explore finding some hidden behavior in a network. So, like in your method, you input like a real image to a network, and you see which feature are activated via your use of a saliency map and the features to get this masked image. But could it be possible, in a sense, to have this input kind of hallucinated or to be some nonsense, which could maybe be used to highlight some problem behavior in the network, like a backdoor or maybe a brittle class? I don't know.
Okay. So I would like to answer this question to two types. The first is I think for our method we do some sanity check, because I think if these images is some nonsense images, it's just some noise, then my salience map should not highlight some meaningful region. It should be black everywhere, or highlight everywhere. Otherwise, our method was not is not fairness enough. So basically, I think this if a good explanation should not explain if there is nothing in the images, it should not highlight the specific region. And according to our sanity check, or according to this philosophy, if there is just random images, our Salience map won't give you some information. It also give you some very random Salience map. It's just a black everywhere. This is one thing. Another thing you are talking is like if we could make some images which is very specific to some target class. So that would be more like the explanation to other class. It's like called the hidden semantic I mentioned before. So this method is they trying to, for instance, they make the most typical images for the banana, for instance, and to see what's really the network then about banana. There actually exists some work to doing that. And I remember actually they just have some curve shape as a typical banana. It's also a very interesting observation.
Okay, thanks.
You're welcome.
Other questions? In the room?
Yes, I saw one people raise the hands, but
Okay,
I don't know how to open the microphone.
Who raised the hand?
It's too small.
Okay.
Everyone just cannot open the microphone.
Okay, so I'm going to ask one question, and meanwhile, Hanwei,
Okay.
you've been showing examples that use one single image. Okay, and in this case, we understand that you, one way or the other, find the more important pixels. That's you know that's very nice. What happens if I want to get an explanation about the class overall? It's nice to see why this particular bird has been classified as a bird, but maybe there are some properties on birds that I would like to understand. So what happens when you move upward?
Yeah, actually, that's actually there are lots of methods to do that. I think it's, for instance, the prototype methods. They trying to find some. So it's like they trying to group some. So it's like they put some constraint in the features, and they force every features learn some part of the features for the typical class, and then they also trying to put some hierarchy to the different features. And I think this is belong to another type of the explanation. No, it's more like the prototype one, or some semantic, hidden semantic maybe also.
Okay. Some other questions? Okay. Yes, I see you, Karen. It's but I don't know why it's not working. I think you have the hand on the sound to put it back. You got to press on the little button on this square. Oh. Otherwise, you just
Hello, hello.
way.
Yeah, we're hearing you.
Can you hear us?
Yes.
Yes.
Yeah, actually, the microphone is not working for everyone. So we had other questions in the room, but yeah. So I might ask a question about the sensitivity of your method to overfitting and its applicability to different architecture and data sets.
So your question is about how I make sure it's not overfitting, right?
No, it is the voice.
Sorry, Karis, can you repeat your question? I'm not sure if I understand correctly. You are talking about overfitting. you are seeing the network overfitting or my explanation method overfitting.
So yes, the question is about what's the effect of overfitting on your method.
Okay.
And the second one is that the applicability of your method and the sensitivity on different architecture and data sets.
Okay. So for the data set, actually in our paper, we try different architecture like RaceNet, VGG, and also we try some transformer. And for the data, we try some ImageNet, and then we try some medical data also. So I think according to the experimental performance, and I think it's quite adapted to different data sets and different network architecture. And also you mentioned about the overfitting of the optimization of my methods. Actually, we also investigate the convergency and the effects of different learning rates. And according to the rates, I think there is I think there is no overfitting. We're just trying to optimize the interpretability loss of it. And also these things is passed to the sanity check of the network. So we didn't see the clean clues to say there exists some overfitting.
Okay, thank you. So one last question from my side. Is there a standard for evaluating the different ad hoc attention methods?
Actually, this is an annoying part, because in this work I show two sets of the evaluation: the average drop, average gain, and average increase. This is evaluation metrics is most likely by the people from the computer vision. It's the most widely used one, especially in CAM-based methods. And the insertion deletion is also very common and wide used methods. It's not only in CAM-based methods, also on the other XAI people. But as I said, I evaluate all the existing interpretability metrics. The only concern from me is I don't think all these methods are good enough. So it's a reason why I think for the future work, maybe we should improve all these metrics to evaluate the interpretability. And also, it's very interesting there. Recent year, this is common sense of the researchers in this domain. There are quite a lot of methods to say evaluate the evaluation metrics of interpretability.
Okay, thank you. It was clear so about the standard evaluation. We might have one last question in the room by Victor.
Vas-y.
Okay, hello. Thank you for the talk first. I have maybe one other stupid question, but is it possible that one way to explain why OptiCAM is working better than the other CAM method, that the zone considered after masking the image is much larger with OptiCAM than with the other CAM methods? So maybe something like the other CAM methods are not, they are considering too small zones, and that is just why they can't grab all the information, and why the prediction then is also, of course, bit worse.
Yes, actually, this is a huge problem for us because we have a quite nice score outperform in the average drop, average gain, average increase. It's not a surprise, because thinking about what is our interpretability loss, we're trying to make the salience map to help to increase the confidence of prediction to the target class. And that is kind of aligned to the metrics, to these metrics. So of course, we will achieve very remarkable results in these metrics. And also, when we look at the salience map, it's true that we take the background. So here the thing is, then there is become more like a philosophy problem to us, because there are some people will argue that they think the good interpretability means they found more region of the object. But we already proved, according to the very simple experiments with the bounding box, actually it's not how the networks works. We think by our OptiCAM, we're just trying to optimize, to let it to optimize to find a salience map, which will optimize some definition of the interpretability we agree with. Is like this salience map will help to improve the performance of the network. And then we think this is the region how the network to make the decision. But maybe, so it's like luckily when we look at it, we found this is because it's also look at the background. So we think it's exactly explain how the network to work, because if they're chaining not only because for instance the bicycles, if we're looking at the chaining data, most of the case this tri-cycle will appear with some children and some humans. So training with that, I think it's fair enough. They think the humans also important pixel to support this decision. This is my understanding. But also the interpretability is also related to how the human think, the human cognition. This is also if we think in this way, and we think the average drop, average increase, average gain is most reliable metrics, then we would see our OptiCAM provide the best performance. But it also depends how people to define the interpretability. If they just define them like we don't care about what it provides the most information for the network, we just want to find the object. And it's like it's better like some segmentation or localization of the objects. Then maybe to that sense, our OptiCAM is a failure. So I think it's really depends on how you define the interpretability.
Thank you very much.
Some other questions somewhere? Otherwise, thank you again, Hanwei, for giving this interesting talk. And we hope to see you soon with us. Right? OK.
OK, thank you.
Merci à tout le monde. À bientôt. Au revoir.
Au revoir.
Au revoir.
Bye bye.
Bye.